Welcome to the second example of SUVAT equation applications with free-fall objects. In this second scenario, we have an object that's being projected upwards with a velocity of 6 meters per second at an elevated height of 7 meters above the ground. We're going to examine 4 things in this example. First task is to determine the time it takes for this ball to reach the peak of its trajectory. Second task is to determine the maximum height that the ball is displaced above its starting position. Third task is to work out the total time of this ball's journey from launch to when it hits the ground. And finally, our fourth task is to work out what is the impact velocity of this ball upon striking the ground. So first of all, let's work out what is the height it reaches, its peak height. So we're following a 3-step process. Step number 1, let's state our variables. In fact, before we do that, let's align or allocate direction. We're going to take the initial velocity of this object as a positive direction. So for the purpose of this question, all motion upwards will be considered positive. There's my abbreviation for positive. So we have an initial upwards velocity of 6 meters per second. The acceleration of all objects is back towards the Earth. So it's in the opposing direction. So the ball is accelerated at negative 10 meters per second. We're asked to find the maximum height of the object from its starting position. Now looking at these variables, we appear to be one variable short. We have a u, we have an a. We're trying to find s, the displacement, which means to solve this equation, we need either a v or a t. Now nowhere in what I've described so far have I mentioned any time. Can you see how we can use v, the final velocity, in this scenario? If we're to analyse a ball that starts at this position and goes right up to the peak, and that's where we stop our analysis. At that peak location, for a split second, we have what we call an instantaneous velocity of 0. So if we analyse the scenario from the start just to the top, that will give us all the variables we need to solve this particular question to work out the maximum displacement. So there's our variables. Number 2, let's select an equation. So we have u, a, v and s. The one variable that's missing is t. So we'll use this equation. It's the only equation that has a u, a, v and an s. The third and final step is simply to substitute those values into the equation and solve for the unknown value for displacement. Let's now take our values and substitute into the equation. Let's now simplify that. Now we'd like to find s by itself. I recommend we add that negative 20s to the left-hand side to give us all positive values. Finally, to get s by itself, it's currently times 20. Let's divide both sides by 20. So there we have it. The height the ball will reach at an initial velocity of 6 meters per second is 1.8 meters above its starting position. Task number 2. Let's now determine the time it takes from its initial position to its peak maximum height, following a 3-step process. Let's again write down the variables. There we have our 4 variables. We're taking the direction of the initial velocity upwards as positive. So we have an initial velocity of 6 meters per second. We have an acceleration opposing that going downwards towards the ground. So it has a value of negative 10 meters per second squared. The velocity right at the top, at its peak trajectory, is 0 meters per second. It's an instantaneous velocity for that split second. And we want to calculate the time it takes to get to that point. Now, we're not going to use the displacement that we calculated previously. Just in case there's an error, we're going to stick with the values we know and choose our appropriate equation. So, an equation that has u, a, v and t and is missing s. It's missing s. It is simply v equals u plus at. So let's write that down. Our third and final step is to substitute our values into this equation and solve for the unknown t. So let's do that. Once again, we get to this particular point. I don't want to be dealing with negative time, so I'm going to add that across to the left-hand side. At the moment, we have 10 times t equals 6. To get rid of the times 10, we'll divide both sides by 10. So there you have it. The time taken for a ball to be thrown with an initial velocity of 6 meters per second upwards against gravity to its peak point will be 0.6 seconds. Our third question is to work out the total time of this projection. So at this point in time, we know from the starting position to the top. So to date, we know that from the starting position right at the top of the projection, we have a time of 0.06 per second and a displacement of 1.8 meters. If we could work out the time it takes to fall from this peak to zero, then add it to the time it took to rise to that peak position, we'd have the total time. So first of all, let's work out the time it takes from its maximum height to reach the ground. Once again, let's consider the direction of the initial velocity as positive. Okay, our variables are as follows. So we have an initial speed at the top of 0. It's an instantaneous speed of 0. We're accelerating downwards at 10 meters per second, and that's positive as well. The total displacement being travelled is the sum of the 1.8 meters plus the 7 meters. So this ball is going to fall a total of 8.8 meters. And we're trying to work out the time it takes for it to do so, from the top to the bottom. We have the variables u, a, s and t, but we don't have the final velocity v. The SUVAT equations that don't have v is s equals ut plus a half at squared. So that's the equation we're going to use. Let's now substitute these values into our equation and solve. So we reach the point where we have 8.8 equals 5t squared. Let's divide both sides by 5. So we now have an expression with t squared. Let's now take the square root of both sides to determine what the value of t is. So we've discovered the time it takes for a ball to fall at an initial speed of 0, a distance of 8.8 meters, is 1.3 seconds. However, the question asks, what's the total time of this projection? So the total time will be the 1.3 seconds plus the 0.6 seconds that we previously calculated. So this projecting object with an initial speed of 6 meters per second, fired from an elevation of 7 meters, will take a total of 1.9 seconds to elevate to the top and drop back down to ground level. The fourth and final question was to work out what is the impact velocity. Following on from our previous calculation, let's examine from the top position to the bottom, a complete free fall. And because the initial velocity of this section of motion is heading downwards, we'll consider all directions downwards as positive values. So let's fill in the variables. Okay, we're starting at the top. It's got an initial speed of 0. We're then accelerating due to gravity at a rate of 10 meters per second. We have a total displacement from the top to the bottom of 7.7 plus 1.8, which gives us 8.8 meters. And we want to know what is the impact velocity right at the bottom. Impact velocity is a velocity just before it hits the ground. And so that's v, our unknown. Now, let's choose an equation from our SUVAT equations that consists of a u, a, s and v, but not a t. Down the bottom, the one that's missing the t is v squared equals u squared plus 2as. So let's write that down. Our final requirement is to substitute these values into this equation and solve for the unknown value v. V is our unknown quantity, so we leave that as the letter v and we substitute everything else in. Let's simplify this. So v squared is equal to 176. We take the square root of both sides to find out what v is. So the impact velocity of an object being thrown at 6 meters per second straight up at an elevation of 7 meters after it goes up and comes all the way back down again will be 13.3 meters per second.
You've been watching a Juddy Productions video. If you've enjoyed and indeed learnt something from this video, then please remember to like, share, comment and subscribe. And as always, thanks for watching.